right, so we're still in Le Châtelier's principle, but now we're going to look at the effect of temperature on the equilibrium of the system. So again, the beginning sentence is very easy. If the temperature is decreased, the reaction will shift to increase the heat or the temperature of your system. If temperature is increased, the reaction will shift to decrease, right? We always want to counteract the change. So the easiest way to look at these is to put the heat term as either a reactant or a product, and then just treat it as you would a concentration question. In this example, if the temperature was decreased, so if we're decreasing the heat, you would want to make more. Your equilibrium would shift left for there to be more heat produced. This would increase the amount of heat energy. When you do that, when you shift left to make more heat, you would also decrease the concentration of nitrogen and hydrogen while increasing the concentration of ammonia. So here's our diagram. Again, we have our three species coming in at equilibrium. This is where equilibrium is disturbed. In this example, your mixture is cooled. The temperature is decreased. So my reaction shifted left, and I had a decrease in the concentration of hydrogen and nitrogen, and I had an increase in the concentration of ammonia until my equilibrium was reached and my concentrations were constant. So in these diagrams, there wasn't an immediate change, like no sudden spike, but everything shifted because of the change in temperature. If the temperature was increased, right, think of it as having more heat, you're going to shift to the right to decrease the amount of heat energy. What will that do? Well, if I shift to the right, I'm going to decrease the concentration of ammonia and increase the concentration of nitrogen and hydrogen. From a concentration or an equilibrium graph, you would have concentration as a function of time. Again, you'd have ammonia, hydrogen, and nitrogen. Doesn't matter really where you put them. I kind of like this diagram better than the other one, just because the reactants are together and the products are together. Okay, so we're going to say at this point in time, the temperature is increased. So let's just say warmed. We shift to use up that heat, so we shifted to the right. That is going to decrease my concentration of ammonia until it reaches equilibrium, and it's going to increase my concentration of nitrogen and hydrogen. And then you're going to have a spot where you reach equilibrium where the concentrations will be constant again. Okay, so it's just shifting where equilibrium is. So you're at equilibrium, everybody's happy, something happens, and then the reaction goes, I want to get back to equilibrium. And so then it shifts to get back to the state of equilibrium. And again, we will quantify this in a bit. So let's do an example. This time I have nitrogen dioxide, which we've seen before. It is a red-brown liquid, and it can form dinitrogen tetroxide, but when it does it, it releases heat. If the temperature is increased, which way will equilibrium shift? Okay, so maybe pause the video, just answer these questions and think about what the color change would be. Is it going to get more brown or more colorless or less brown? If the temperature is increased, you are going to shift left to decrease the temperature, right? Use it up, consume it. And since we're shifting left, we're going more towards the red-brown side. The color will be more brown. It will get darker. If the temperature is decreased, the equilibrium will shift to the right to increase the temperature and produce more heat, but you're going more towards the colorless liquid. So the color will be more colorless, or I could have just said will be lighter, right? Now, I've got a really great video showing this happening. So let me just pause this.
The conversion of red-brown NO2 to colorless N2O4 is an exothermic reaction. we're going to use Le Châtelier's principle to predict the shift of the reaction with respect to temperature and also the color. Because this reaction is exothermic, heat is a product. Therefore, adding more heat to the reaction will shift it towards the red-brown reactants, the NO2. Placing the other tube in cold water is the same as removing heat from the reaction, so removing a product. That will result in the conversion of NO2 to the colorless N2O4.
So that video reinforced what we were talking about. When the temperature was increased, the equilibrium shifted left and the test tube became a darker brown. When the temperature was decreased by putting that test tube into the ice bath, the equilibrium shifted right to make more heat or produce more heat. And so it got to be a lighter brown. It reached more towards being colorless, right? You had more colorless species produced, so then it diluted the color. The next thing I want you to do is I want you to just try a couple on your own. So I want you to pause the video and think about which way would the equilibrium would shift if the temperature was increased and decreased for this reaction. So hopefully if the temperature was increased, you went away from the heat term, right? You consumed it. So the equilibrium would shift towards the products. Or you could say that it's going to shift to the right. So there's a couple ways that these can be like worded, right? So they could say which way would the equilibrium shift or which side would be favored. If the temperature was decreased, you'd want to go towards the reactants. The reactants would be favored, which is a shift to the left. Just a couple notes before we leave temperature. Number one is that this has to be a sustained temperature change. If we went back to that video and we said, okay, now let's take those test tubes back out of the water baths, they would go back to being the same temperature as they were before. In other words, they would match. So if you put them back to room temperature, they're going to shift their equilibrium back to where they were. So a sustained temperature change is required to establish a new equilibrium. Otherwise, you will get a brief change and it will return to its original state. And the other one is just something that we have to keep saying all throughout this course, which is that when you increase temperature, more molecules have sufficient energy for a successful collision, so it will also increase the reaction rate so that equilibrium will be reached faster. All right.